tracing the universe from Newton to modern cosmology. A. From Earth-centered thinking to modern astronomy. For thousands of years, humans attempted to explain the heavens using relatively simple models. Ancient astronomers generally relied on a geocentric model, according to which Earth occupied the center of the universe. The later development of the heliocentric model represented a dramatic change in scientific thinking, as the Sun was placed at the center of the planetary system. The laws of Isaac Newton subsequently provided a mathematical explanation for the gravitational pull that governs the movement of celestial bodies. Newton's work laid the foundation for later discoveries, including the discoveries of Albert Einstein, which fundamentally changed scientists' understanding of gravity, space and time. B. The life and energy of stars. Modern astronomers regard a star as a luminous celestial body whose energy is largely produced through a nuclear fusion reaction. The resulting radiation emission travels across space and can eventually be detected by telescopes on or around Earth. Scientists can analyze the absorption spectrum of starlight and detect light wavelengths to identify the elements present in a star's atmosphere. They can also measure absolute magnitude, allowing them to compare the intrinsic brightness of different stars. The stellar evolution process varies according to the mass of a star. A massive supergiant star, for example, may eventually expand into a red giant and later trigger a supernova. After such an event, the remaining material may undergo further transformation and eventually cool into a white dwarf. These processes also contribute to the enrichment of the interstellar medium, from which future generations of stars and planets may form. C. The formation of planetary systems. Astronomers believe that planets develop from material surrounding young stars. Within a primordial gas cloud, tiny solid objects called planetesimals can gradually collide and coalesce from planetesimals into larger bodies. Over extremely long periods, these bodies can form planets, including terrestrial planets such as Earth. Once a planet has formed, its movement is influenced by the gravitational pull of its parent star. Under suitable conditions, it may maintain a stable elliptical orbit. The conservation of momentum also plays an important role in explaining the movement of matter throughout planetary systems. Some planets possess a planetary magnetic field, which can interact with charged particles and electromagnetic radiation. D. Observing the solar system. Astronomers continue to explore the solar system using increasingly sophisticated instruments. The Sun itself is a major object of study. Scientists observe the solar corona, investigate an intense solar flare, and monitor sunspot cycles in order to understand changes in solar activity. Solar activity is closely related to the electromagnetic environment surrounding the Sun. The force of electromagnetism influences charged particles and can produce radiation across different parts of the electromagnetic spectrum. Researchers therefore examine emissions at frequencies including high radio frequency. Observation is not limited to the Sun. An astronomer may observe a bright nova, spot a distant constellation, or examine other celestial objects from Earth. However, observations can be affected by atmospheric conditions. High atmospheric density, for example, can influence the way light travels through the atmosphere, making certain astronomical observations more difficult. Measuring the universe. One of the greatest challenges in astronomy is determining how far away celestial objects are. A stellar parallax measurement can be used to estimate the distance to relatively nearby stars. For objects much farther away, astronomers may measure cosmic redshift to investigate their movement and the expansion of the universe. Modern instruments have greatly expanded this ability. A space-based telescope can observe objects without having to look through the entire atmosphere of Earth. Such instruments allow researchers to investigate the structure of a spiral galaxy, examine objects near the edge of the Milky Way, and collect information from extremely distant regions of space. Astronomers must also deal with space debris, which can pose a danger to satellites and spacecraft. As human activity in space increases, monitoring such material has become an increasingly important aspect of space exploration. F. Einstein, Space-Time and Extreme Objects. The general theory of relativity introduced a revolutionary explanation of gravity. According to this theory, gravity can be understood in terms of the curvature of space-time. This framework has helped scientists investigate some of the most extreme objects in the universe, including a supermassive black hole. A black hole can have an enormous gravitational influence on its surrounding. Scientists use observations of stars, gas and radiation around these objects to investigate their property. Such research contributes to the broader principles of modern cosmology, which attempt to explain the origin, structure, and evolution of the universe. At much smaller scales, physicists study the behavior of the subatomic particle. Some experiments investigate processes involving antimatter, including the annihilation of antimatter, in which matter and antimatter interact and release energy. Scientists also investigate the process of nuclear fission, which differs from nuclear fusion because a heavy atomic nucleus is divided rather than lighter nuclei being combined. G. The origin and future of the universe. The study of cosmology extends far beyond individual stars and galaxies. Scientists search for dark matter because the gravitational behavior of galaxies cannot be fully explained by the matter that can be directly observed. Dark matter, therefore, remains one of the major unanswered questions in modern astronomy. Other questions concern the origin and ultimate structure of the universe. Observational evidence continues to support the Big Bang theory, which proposes that the universe has evolved from an extremely hot and dense early state. However, cosmologists have also developed alternative ideas, including a model of a closed universe and the theory of the multiverse. As technology develops, scientists hope to explore the deep cosmos in greater detail. Some highly speculative theories even suggest that it might theoretically be possible to travel through a wormhole, although this remains far beyond current technological capabilities.